Hi guys, here's another video about the CSS Pure Mathematics Exam from 2023, and this is the last question of section B. This is question 6, item B. This question has two parts. For the first one, it asks us to find an equation of a normal line to the hyperbola given by this equation: x squared over a squared minus y squared over b squared equals 1, and it asks us to find the normal line in this form: ax cosine theta plus by cotangent theta equals a squared plus b squared. For the second part, we are asked to prove that this normal line is external bisector of the angle between the focal distances of its foot, meaning the point at which the normal line intersects the curve. So let's begin by solving the first part. So we call this hyperbola C, it's a curve, and we parameterize it. So recalling a parameterization of a hyperbola can be obtained by this function gamma, defined in this set I, which is the union of these two intervals, minus pi over 2 to pi over 2 union pi over 2, 3 pi's over 2. Okay, so we define this curve this way. So gamma of theta or theta is a times secant theta and b tangent theta. So this is a parameterization of the hyperbola. It's pretty standard to check this. So now, since we want to find the normal line, we will use this parameterization to find a tangent vector and a normal vector, and with this normal vector we'll be able to find an equation for the normal line. So first we are going to take the derivative of this curve here. So for any theta in the set y, we have that the derivative of gamma prime of theta is, now the derivative of a secant theta is a secant theta tangent theta, and the derivative of b tangent theta is b secant squared theta. So this is a tangent vector to this curve C, to the hyperbola, at this point gamma of theta. Fine, perfect. Now once we have this, we have to remember one thing. This is a plane curve, so it is a plane. So if we have a tangent vector, if we find an orthogonal vector to this one, then this orthogonal vector is normal to the curve. Okay, so, and since we're in a plane, a two-dimensional space, it's easy to find. Whenever I have a vector of the form xy, I know that the vector minus yx, for example, is perpendicular to this vector. So this is what we are gonna do. So we take this vector v of theta, b secant squared theta, and minus a secant theta times tangent theta. So I reverse the coordinates of the tangent vector and I put a minus in the second coordinate. Here I reverse this, I change this here, and I put a minus. So if we take the dot product of these vectors, we'll see that it's 0. So this vector v is indeed perpendicular to the tangent vector, and therefore it gives us a normal direction, which is what we want. So now we know a vector which gives the direction of the normal line. So now in order to find the normal line, we already have a direction vector. We are going to use the vector expression of a line, a vector parameterization of a line, to find a parametric equation for this normal line. So as I said, this vector v is perpendicular to gamma prime, so it is normal to C, to the curve C, to the hyperbola at this point gamma of theta. And now to find the parameterization of the normal line to the hyperbola at this point gamma of theta, we can use this one, beta, defined this way. It's just gamma of theta plus t times the vector. We call that this v theta is a fixed vector. It's a fixed because theta is fixed. We are working only in the point gamma of theta. And also the gamma of theta is a point, is a fixed. So we can write this in coordinates here. So we have the point gamma of theta is a secant theta, and its second coordinate is b tangent theta here. And now we add t times v of theta. So here we have this b secant square theta multiplied by t, and here we have the minus a secant theta times tangent theta multiplied by t. And here, this is the coordinate x of my parametrization, and this is the coordinate y of my parametrization. Perfect. Now, what we are going to do, we are going to solve this expression here. Since we have x of t equals this one, we are going to solve this expression for t. So, since we have this expression, we will solve this for t. It's pretty easy. We just add minus a secant theta to both sides, and then we divide both sides by b secant squared of theta to obtain t. So we get that t equals x minus a secant theta divided by b secant squared of theta. And perfect. What should we do now? Now we are going to use this value of t. We are going to plug this in the other equation for y, because what we want to do is to find a Cartesian equation for this line, this normal line, in order to solve the problem. We already have a parametric expression for the line, but we are interested in a Cartesian equation. So we get this t, and we plug it in this expression here for y. So we take this t here, and we plug it in here. So plugging this t into this equation, we obtain this expression. So we have here y equals b times tangent theta minus a times secant theta times tangent theta multiplied by the t we obtained. So x minus a secant theta over b secant squared theta. Now we are going to simplify a bit the stuff. We have this. So if we can multiply and divide by b here, we don't change anything here, and we now multiply. We have here this, since we have a minus here, this minus with this minus becomes a plus, and this minus with this x becomes a minus. So here we have, and since we had secant squared here, we can cancel this secant with this secant. And since we had tangent, so the tangent, which is sine over cosine, and here we have a secant, which is 1 over cosine. These cosines will cancel out too. Okay, and we are going to obtain a squared times tangent theta minus ax sine theta. So this is, we are almost done for this part. And now we are going to put everything over the same denominator. Since we have b squared plus a squared multiplied by tangent theta, we put these two together, and we have this, the minus ax sine theta stays the same. So you obtain this. So just by multiplying both sides of this y equals this one by b, we obtain ax sine theta plus by equals a squared plus b squared multiplied by tangent theta. Finally, we divide both sides by tangent theta, and we obtain ax cosine theta plus by cotangent theta equals a squared plus b theta, which is what we wanted. So it's not a hard problem. It's a bit complicated saying it in words. It's easier just to read through all the equations. This is why I put all the calculations in there. Okay, so maybe you can pause the video, take a look at it, and do it by hand to see if you manage to understand all the calculations. Okay, perfect. Now we are going to go to the second part. So once we have the first part, we are going to solve second part. So the second part asks us to show that this normal line whose equation we found here is external bisector of the angle formed by the lines which connect the foci of the hyperbola to the point where the line is normal. So we will see with some drawing. It's better to see with pictures than just saying it. Okay, so let's go. So first, as I said, let's understand a bit the problem by a sketch. So here's a sketch. So recall that we have this hyperbola with this equation, x squared over a squared minus y squared over b squared equals 1. So this hyperbola has this form. So here we have the minus a0. It's the point where the hyperbola cuts the x-axis for on this side, and on the other side it cuts in this other point a0. We also have these points here, minus c0 and c0. Those are the foci of the hyperbola. And a and c are related, and b are related by this equation. So c squared equals a squared plus b squared, or which is the same as c equals square root of a squared plus b squared, because all these numbers a, b, and c must be positive. Okay, so this is our hyperbola. But now let's see. So we're gonna recall that we parameterize it by a secant theta and b tangent theta. So we are gonna take up any point in this hyperbola can be written in this form, where theta is in the interval in the set I, which is the union of two intervals as we define the parameterization. So here we go. So here I wrote a lot, so this maybe you can pause the video and see what is written here, but with the picture I have below, it's easier to understand. So here's the picture. We have this point here, which is the point a secant theta b tangent theta. It's a point in the hyperbola. And we take the line connecting this focus here, the focus minus c0 to the point, and this other line here connecting the focus c0 to the point. We have these two lines. So these two lines intersect in the point, a secant theta, b tangent theta, and they form a triangle. So we have this triangle here, whose side we have these sides here, which connecting the points minus c0, c0, and this line segment and this line segment. So we have a triangle. And we have this external angle here in red. And this is the angle we want to show, and in blue, I drew the normal line. So we want to show that this normal line bisects this angle. Namely, we want to show that this angle here is the same as this angle here. So I must comment that actually you should also in any way show that indeed this line cuts this angle. So you should be able to show that, for example, this line doesn't cut the other angle. So it's not hard to show it, because obviously the tangent line must be the one which intersects the triangle by the inside part of the triangle, and the normal line should be outside this triangle. Okay, this is something we won't do, but it's kind of obvious geometrically. You can try drawing this at any point of the hyperbola, and you get that this line must be external to this triangle. Okay, so we have that this line, this normal line, cuts this angle in two parts. And we are gonna try to find a relation between these angles and see what we can do. So let's go. So first, it's an important thing. We are going to use a formula for which relates the angle formed by lines and their angular coefficients, their slopes. So first I'm going to calculate the slopes of this line here, the line connecting the focus minus C0 and the point, A secant theta B tangent theta, and I'm going to find the slope of the line which intersects the focus C0 and the point, A secant theta B tangent theta. Okay, so let's do it. So I'm going to call the first line, I'm going to suppose it has this equation mx plus n, and the other line has the equation m prime x plus n prime. So as I mentioned, our goal here is not to find the equation of the lines. I'm just interested in finding m and m prime, so just the slopes. So it's not hard to see because we have this equation. Since this line with this equation mx plus n contains this point here and this point here, all I need to do is plug these 2 points in the equation. So I put here in this x a secant theta plus n must be tangent theta, and I put here in this x minus c plus n, it must be 0. And I do a similar thing for the second line. So I have this equation here, and I put a secant theta n prime times a secant theta plus n prime equals b tangent theta, and then m prime times c plus n prime equals 0. Perfect. Now what I'm going to do is subtract. I take this first equation minus this one because I'm interested in find m. And I do the same with this one. I take this equation minus this equation. And what I get is m equals b sine theta over a plus c cosine theta, and m prime is b sine theta over a minus c cosine theta. Perfect. So what should we do now? Okay, now we are going to use another thing we're going to use is we found this equation for the normal line in this form: ax cosine theta plus by cotangent theta equals a squared plus b squared. So if we solve this equation for y, we obtain that y equals, we just put y equals, let's see, ax, we just put this one, we get by cotangent theta equals minus ax cosine theta plus a squared plus b squared. Then we divide it by b cotangent theta, and we obtain what we wanted. I'm just interested in the slope. We obtain that the slope of this line is minus a over b times sine theta. Okay, perfect. So, and this is what we are going to use. So we have the slope of 3 lines, and now we are going to, and this will be useful to us because this will allow us to find the angles we want to find above. So now I'm going to call alpha and beta these 2 angles. This is alpha and this is beta. Okay. And if we look at these angles, their sum is the external angle of a triangle, since we know that the sum of the angles of a triangle is 180. So, and this angle alpha plus beta, it must be less than 180, because this must be this is the sum. This angle is the sum of this angle and this angle, so it must be less than 180. Okay, perfect. So in particular, what we get is that alpha and beta cannot be obtuse angles. They cannot be both greater than 90 degrees. At least one of them must be less or equal than 90 degrees. Okay, perfect. And so this is what is written here. So we are going to assume that this alpha is acute, so it's less than 90 degrees. So if we took B, we obtain the same. If we assume that beta was smaller than 90 degrees, we would obtain the same result. So we are going to assume that alpha is less than 90 degrees, or more pi over 2 if we're talking radians. So we're assuming that, and now we are going to recall the formula I mentioned, which tells us the angle between two lines, the acute angle between two lines. So recall that if we have two intersecting lines which are non-perpendicular with Cartesian equations of this form, m1x plus n1 and m2x plus n2, the acute angle between them is given by this formula. The tangent of this angle is given by this formula. So I take the difference between their slopes, and I divide it by 1 plus the product, and I take the absolute value. Okay? So this equation this formula is the one we are going to use to solve the problem. So now comes a bit of calculation. So alpha I assumed alpha is acute. So this means that, let's take a look at alpha here. This means that since alpha, if we look at alpha, we have this line here and the normal line. Since I'm assuming alpha is acute, what we get is this is indeed the acute angle between this line, the normal line, and this line connecting the focus C0 to the point A secant theta, B tangent theta. Okay? And so I know a formula to find the tangent of this angle, to find the tangent of alpha. So I use this formula here. So I know that tangent alpha is, now I know the slope for this line, for the line, the normal line is this one. And I know the slope of the line connecting the focus C0 to the point, to the foot of the normal line. So this one. So I apply the formula. So I'm not dwell much in the calculations. You can pause the video and take a look at the calculations. So just here, I just see that I plug the slopes here. So I put here b sine theta over a minus c cosine theta, and here plug minus a over b sine theta, and here I plug the same. So we just make a bunch of calculations. There's lots of stuff are going to cancel out, and finally we are going to obtain the absolute value of c over b times tangent theta. Perfect. We found the tangent of alpha. Now we're gonna deal with beta. Okay, so now if we call gamma the acute angle between the normal line and the line connecting minus C0 to the line, we can use the formula we used before. Just let's take a look a bit in the drawing. Here I had two angles. So suppose this angle beta, if it was an acute angle, supposing it was acute, so the angle between the blue line, the normal line, and this line here, the tangent of this angle beta would be expressed by the formula we had before. But suppose that maybe this angle would be obtuse. It would be greater than 90 degrees. So, but if this angle were greater than 90 degrees, then the acute angle between these two lines, this blue line, the normal line, and this line would be pi minus beta. This would be an acute angle. And the tangent of pi minus beta would satisfy the equation using the slopes of the lines. But now recall that the tangent of pi minus beta is minus tangent of beta. So we have a relation for this between these angles and the slopes. So we are gonna assume, we don't know yet if beta is acute or not. So we call this the angle between the blue line, the acute angle between the normal line and this line here connecting the focus minus C0 and the point A secant theta B tangent theta. We call this the acute angle between these lines gamma, okay? And once we call this gamma, as I mentioned before, there are two options for gamma. If beta is acute, gamma equals beta. On the other side, if beta is obtuse, then gamma must be pi minus beta. Now we use the formula, the same formula we used here. This formula, we use it for the other two lines. So now we recall that the slope of this line here, connecting the focus minus C0 and this point, is this one, is B sine theta over A plus C cosine theta. And again, the slope of the normal line is this one, minus A over B sine theta. So we get that the tangent gamma is given by this formula. Again, we do a bunch of calculations, so you can pause the video and see if you understand all the calculations. And we obtain again that the tangent of gamma is absolute value of C over B times tangent theta, which is the same value you obtain for tangent alpha. Okay, we are almost done. Now, what we get here. So since by hypothesis alpha is acute and gamma is acute, so the tangent of both angles are the same and they are acute, so they must be the same angle. This tells us that gamma, since tangent gamma equals tangent alpha, this tells us that both angles are the same. Okay? So if we had that beta were pi minus gamma, then adding these two angles, alpha plus beta, we would obtain pi. But this cannot happen because alpha plus beta must be smaller than pi, smaller than 180 degrees. This tells us that alpha must be acute and that beta equals gamma equals alpha. And we obtain what we wanted. So the normal line indeed bisects the angle alpha plus beta, and alpha equals beta. And you're done. It wasn't a hard problem, kind of cumbersome, but not hard. So you can pause the video, make all the calculations, see if you understand it. And if you have any doubts or any comments, please tell me. I hope you enjoyed the video. Thank you very much. And I hope to make more videos soon. So don't forget to subscribe to the channel and give me a thumbs up. Thank you very much. Bye.